So if the energy of the gamma we've just calculated is the maximum energy the photon can have when it's coming directly towards you as the observer, the other photon, which is emitted back to back, must be going directly away from you. And so its momentum is going to have this, is going to contribute a minus sign in the expression that we got before for the total energy in the Lorentz transformation. The easiest way to think about this problem, though, is just to think about simple energy conservation. We know that the total energy available before the collision is 1 GeV. That's the total energy of the pi meson in the primed frame. We've just calculated that the energy of the maximum energy that a single photon can have if it's emitted directly towards an observer is 995.5 MeV. Now it stands to reason that the other photon, if this is the maximum energy photon, the other photon must be the minimum energy photon. It's moving directly away from you to conserve momentum, therefore it's got the lowest energy it could possibly have, because its motion away from you is going to mean that it's redshifted, so it's going to have less energy than it would have in the frame where the photon, where the pi meson's decaying at rest. So we can just use simple energy conservation to figure out the energy of the other photon, knowing that that energy is going to be the minimum energy a photon can have. So let's do that. So the minimum energy of a photon, E gamma min, is going to be the energy of the pi meson in the primed frame, these are all in the primed frame, minus E gamma prime max, right? Which is going to be E pi minus E pi primed minus the expression for E gamma prime from before, which is E pi primed over 2 plus P pi prime C over 2. And so E gamma prime min equals E pi primed over 2 minus P pi prime C over 2. So we'll just put everything over 2 and write that E gamma prime min is E pi primed minus P pi prime C over 2. Notice the similarity to the other expression. So the first expression, the maximum energy of the emitted pi meson is E pi primed plus P pi primed C over 2, and the minimum energy is E pi primed minus P pi primed C over 2. And again, we can substitute in numbers, so you get the energy of the pi meson in the primed frame, which again is 1000 MeV, minus 991 MeV over 2, and that comes out as 4.5 MeV. And that adds to the energy of the other maximum energy gamma of 995.5 MeV to give you a total of 1 GeV, which is the available energy. So energy is, thank goodness, conserved as usual. And just finally, let's get the maximum photon wavelength from this minimum energy photon. The lowest energy photon is going to have the biggest wavelength. And so again, lambda equals the ratio of Planck's constant to the momentum, which is, using this trick, 2 pi h bar c over pc, which for a photon, E equals pc, so it becomes 2 pi times 0.2 GeV femtometers, which is the value of h bar c in those funny units, divided by the energy of the photon, which is 4.5 MeV. P prime C, I guess, trying to keep my primes straight here. And so that comes out as a much larger number. That comes out as 275 femtometers. So the wavelength, the longest wavelength a photon can have from this collision in the frame where the pi meson has total energy of 1 GeV is 275 femtometers, which is about a factor of 200 greater than the wavelength of the minimum wavelength photon, and that's the answer. Now, I hope you've got from this revision lecture the concepts of energy and momentum conservation. I hope that I've managed to show you how to do a Lorentz transformation in momentum and energy, and I hope that this rather complicated calculation has given you a little bit of insight into doing relativistic calculations with algebra. The other thing which is kind of neat from this example is showing you that beta, V over C for a particle, turns out to be the ratio of the momentum of the particle times c divided by the energy of the particle. That's a useful thing to know. And of course it goes with its sister expression, which is the expression for gamma, which is just the total energy of the particle divided by its rest mass m times c squared. Okay, that's the end of this revision lecture. I'd like to wish everybody the best of luck on the exam next week. None of the questions will be this hard. I thought it was a good idea to go through this question since it was in the tutorials and people probably won't have had a chance to study the question. Maybe they're using it for revision. And if you have further problems with your revision or things you need to know, please don't hesitate to email me and ask me those questions. I'll be keeping an eye on my email towards the end of this week and over the weekend. So again, best of luck in the exam. I hope you choose to do a relativity question, and they'll be easier than this one. So, bye.